little messy. For example, we know that when you have the same base, different exponents, when you're multiplying, you add your exponents together. So it works the same when you have fractional exponents. As long as the bases are the same, you're just adding the exponents. So here, my apologies, didn't blow up very well, did it? Let's write this off the side. Not even one person. When you have the same base, different exponents, when you're multiplying, you're adding your exponents. So you have 3 to the 1/2 times 3 to the 3/2. Well, what's the base in that problem? Number 3. The exponent, they have the same basis, so now those exponents, you just add them together. So it's 1/2 plus 3/2. 4/2, otherwise known as? So your answer would be 9. Now, would this change if these were variables? No, it'd be the same thing, same principle. If it's x to the 1/3 times x to the 2/3, what do you get? X to the 3/3, which is x to the 1st. Okay, same idea. Okay, we're going to slowly work into variables. Today, we're going to basically spend the whole time dealing with numbers again. So we have to learn how to work with them a little bit, how to simplify them out. Same deal here, power to power. When you have power to power, you are multiplying your exponents. So the example they give us is 4 to the 2/3 squared. Is that 2/3? Sorry, that's 3/2. My bad. So that means you're just multiplying your exponents. So what's 3/2 times 2? 3. And 4 cubed is 64. Okay. Power to power, you multiply. Okay. Power to power, you're going to multiply. Again, please make sure when you're writing out your exponents that are fractional, use top-bottom fractions. Okay? Don't use slashes. Slashes are bad. Same deal here. Quantity to an exponent, you're basically distributing the power. Again, this is something that we've done. So if you have, their example they give us here is 9 times 4 to the 1/2 power. Well, that means you're distributing that exponent to both parts within the parentheses. It would be 9 to the 1/2 times 4 to the 1/2. Well, what does 1/2 power mean again? What's the square root of 9? What's the square root of 4? And 3 times 2 is? There you go. All right. We're working with values that are not difficult. As we get larger numbers, you'll start to learn how, this is where we were talking about it yesterday, how do you start searching for 5th degrees? Which values you're looking at. Remember, in class we were talking about when you square something and you square it again. You multiply those two together, you get a 4th power. Then you start looking at the last digits to see what would match itself out. Okay? There's shortcut ways of figuring these things through. Negative exponents, we did this yesterday as well. Whenever you have a negative exponent, it's not happy where it's at, which means you change its location. If it's not happy in the numerator, you send it to the denominator. If it's not happy in the denominator, you send it to the numerator. It works the same with the negative exponents. That does not change. You saw that yesterday with the one problem we did with, what was it, the negative, the number you had, was it 38? I think on the homework, was it 30? Was it 38 or 37? I think I just did that on the board. When you looked at that one where it was negative times the quantity, 25 to the negative, what was it, 3/2? Okay, so that meant that that 25 was unhappy because it had the negative exponent. This was fine, it's just a value of 1 up front. So that's why we moved the 25 down. Okay, that's something we've all dealt with. All right. It works the same way with its negative, the denominator, it moves up. Okay, those goes vice versa. Textbooks don't normally show them both. Plain war, okay, works the same with fractions. Just like we did before. When you're dividing, if you have the same base, different exponents in the numerator and denominator, even if they're a fractional amount, you just have to figure out to play war. Worst case scenario, in this example here, they have 6 to the 5/2, 6 to the 1/2. Well, that one's pretty easy to tell which one's bigger because they have the same denominator. What would happen if they don't have the same denominator? You'd have to find the common, okay? And a lot of times it's going to be like 1/3, like a denominator of 3 and maybe a denominator of 4. So you have to do a little bit of common denominator work. I try not to make it so horribly god-awful, but you will have to, from time to time, find common denominator. So here, who wins? The 5/2 or the 1/2? 5/2. So what's 5/2 subtract 1/2? 4/2. So that stayed positive, so it goes up top. 4/2 is what? And what's 6 squared? There you go. All right. If you wrote 32 after you did all that and figured all that out, well, that would be fine. You know, I'm just using it for somebody else's example. I know that you knew what you were doing. You just made a completely idiotic move. Okay, and that's well within the realm of, yes, you know what you're doing, you just forgot that 6 times 6 is 36. Okay. All right. And also, distributive property works with fractional amounts again. Same thing. If you have junk, bless you, if you have junk to a power, both of those values get distributed in the numerator and denominator. Example here, they have it as 8/27 to the 1/3. That basically just means that you're sending that 1/3 power to both the numerator and the denominator. What does 1/3 power mean again? Cube root. What's the cube root of 8? And the cube root of 27? Okay. And that's where these go. The last one. Yeah. The last one I put in here was the, if it's negative in the bottom, it moves up. We talked about it. I'm not too worried about it. You guys know that. Now, one rule that kind of goes with all of this is that you will never, ever leave fractional amounts in your denominator. Okay? You'll never leave fractional amounts in your denominator. You will be doing a lot of rationalizing. You guys have been doing that all along. Do we ever leave the square root of 2 in the denominator? No. What would you multiply it by? The square root of 2 is top and bottom, right? Well, in essence, what you're doing, what's the square root power? For example, what's square root power again? What's the power? What's the exponent? 1/2. Okay. For example, we never leave radicals in the denominator. Isn't that the exact same thing as saying 2 to the 1/2? Okay. How many more halves do you need to make a whole? 1 more half, don't you? So you would multiply it, because when you have the same base, you multiply to add your exponents. What was 1/2 times 1/2 plus 1/2? Yeah, so you get the, see, that's where you got the, that's why that was working. The square root of 2 times the square root of 2 was 2. Because if you go back to your exponents, the rule was same base, 2, multiplying different, and the exponents, you add them together. That's how the roots, I don't want to say cancel, that's how the roots go away. That's how rationalizing works, all right? What's going to be different for us now is what happens if this is a, let's say it's 3 over the cube root of 2. So it's 2 to the 1/3, very good. You'll find out really fast that it is so much easier when you're dealing with roots to work with them as exponents than they are to work with nth roots, especially with simplifying stuff. It makes it a little bit cleaner. This becomes 2 to the 1/3. Oops, sorry, it's not times. How many more thirds do you need to make a whole? 2/3. What's 2 to the 2/3 divided by 2 to the 2/3? 1. I'm just multiplying it by some factor of 1. It's just a really funky looking factor. All right? What's your denominator become? 2. Good. And the numerator would be 2, oops, sorry, 3, 2. Can I combine those two? Nope, different exponents. All right. We'll get into that idea. I just wanted to show you that real quick while we're talking about it. All right. Other thing we'll wind up doing, oops, let's go one at a time. Sorry.
Yeah.
Let's look at that 5 to the 1/2 times 5 to the 1/4. You know, once you switch it to the to n-throughs, to the exponents, you can get an exponent. I'm not going to have you switch back and forth because that just doesn't mean it. 5 to the 1/2 times 5 to the 1/4. Do they have the same base?
Yeah.
Yes. 5 is the base. Their exponents are different, but we're multiplying, which means I have to add the exponents. It means you got to get the common denominator. What's the common denominator between a 2 and a 4?
4.
Okay. So this is the same thing as saying 5 to the 2/4 times 5 to the 1/4, which gives you, there you go. All right. And you're done. You're just simplifying it through. We just did an example a second ago with that 7 over the 7, I'm sorry, 7 divided by 7 to the 1/3. You could play war with that, because what's the exponent of the numerator? 1, or in our other case, we could say it is 3/3, right? Who wins in that battle of war? The numerator. So what would you do with the exponents? Subtract them. What's 3/3 minus 1/3? 2/3. So you would simplify this one out, since they're the same bases, you can work with the exponents. You would get 7 to the 2/3. All right. That's how these things kind of wind themselves through. So far, so good-ish?
Yeah.
All right. Move this one over here. Do this one next. All right. Let's look at this one. 12 to the 1/3 divided by 4 to the 1/3, all squared. 12 to the 1/3 divided by 4 to the 1/3, all squared. Now, when you had, before we get to this one, when you had what can you do with that?
The cube root of 8.
No, there's square roots here. What can I do there? Do you guys remember what you did with that? Does this ring a bell? Why can you do that? Well, square roots, because what's their exponent? 1/2. They share the same exponent. Okay. So when you had that, if you had this square root divided by a square root, you could create it as one fractional root. Same thing applies here. 12 to the 1/3, 4 to the 1/3, that's the same fractional root, isn't it? So what's 12 divided by 4? 3. So this can simplify on the inside. You get 3 to the 1/3 squared. What do you do then when you have power to power? Multiply. So what's 1/3 times 2? Okay. It works the same way, whether if you have the same fractional exponents, it's kind of like having the same root. And well, actually, it is the same thing as having the same root. It just so happens that it's cube root divided by cube root. That fraction, since it's the same root on top and bottom, there's nothing else in front of it or anything else, it's grouped together, you can just simplify that fraction, right? And it works. Let's put this up. There it goes. All right. Now, that top one, do they have the same bases? No. So can I do anything with their exponents? No. Okay. So what do I do with the exponent on the outside then? Yeah, it's multiplied inside to the other two exponents. So the only thing I can do here is that I distribute my power to both of these. I'm going to get 8 to the 2/2 times 5 to the 2/3. Well, what's 2/2? 1. So do I have to write 2/2? Okay. I can't combine them any further because they have different exponents. And different bases with different exponents. The bottom one, you've got 2 to the 4th times 3 to the 4th, all to the negative 1/4. That means nothing's happening. So what should you do right away? Put a 1 over it. Correct. Automatically flip everything. I'll just here to get 1 over. My exponent is now positive because it switched sides. So when you distribute in that exponent for your power, what's 4 times the 4th? 1. And you do that twice, so you'll wind up with 2 times 3, otherwise known as 1/6. Could you have done that differently? Absolutely. Could I have distributed in that power to power right off the bat and gotten 4 times negative 1/4, we've gotten negative 1. So I would have had 2 to the negative 1 times 3 to the negative 1, and I could have flipped those both independently as well. Okay? It works out either way. It just kind of depends on how you see it as you're going through. Okay? Let's try out the number ones here. There you go. We'll come back to that for a moment. This was one that we had a little issues. I think we're starting to have a little bit of worries with. Okay. Now, we should all know that you should all know your perfect squares all the way through 20.
I do. But I don't know if I don't know. What is this? Yeah, what's the square of 16? No, I mean, squared.
You guys should all know 1 through 20 in terms of your perfect squares. You really should know those. All right? When it comes to the perfect cube, usually you can get away with the first few. What's 2 cubed?
My God.
Now the reason why these work so cleanly is if you know your perfect squares, all you're doing is taking your perfect square and multiplying it by 2. Perfect square, multiplying it by 3, and so on and so on. So if you know your squares through 20, if you need to figure out what's going to be, 7 cubed, you know that it's going to be 49 times 7, which means what's the last digit have to be? A 3. Okay, so we're going with that? Right? So the idea as you go through these things, you start to kind of fudge your way through it by understanding place value, by understanding how the numbers work. Okay? If you had to do 7 to the 4th, what's the last digit going to be? Yeah. What's the last digit going to have to be? 1. A 1, which means 7 to the 5th has to end in a 7.
Oh, I see. Wait,
All right. Do you agree
Oh.
that 7 squared times 7 squared is 7 to the 4th? Okay, that's 49 times 49. When you multiply it out, the last digit has to end in a 1. Okay? So I don't care what those digits are, but I know that 7 to the 5th means I have to multiply it again by another 7, which means the last digit has to be 7. Which means 7 to the 6th is going to end in a 9. Will end in the 9. 7 to the 7th is going to end in a 3. 7 to the 8th is going to end in a 1. And then it rotates itself through. See, that's why if you know your first couple, you can make and generate the rest of them by figuring out what the last digit's going to be. Okay? And that'll help you to simplify higher degree roots. Yes, ma'am?
You're not listening.
I'm sorry. All right. So what we're going to do here is we're going to start fishing around to figure out, well, is there a perfect cube that I can try and get into 108? All right. So first thing you can do is see if you can divide it by 8. Does 8 go into 10?
No. Yes. That's not good.
How many are left over? 2. Does 8 go into 28?
No.
Okay. Cleanly.
Oh, not clean.
Okay, you're looking for clean. So, again, as you start looking through, we're trying to figure out, is there a way that we could get something to work? So, what is, if you look at breaking it apart then, 108 is, what happens if you cut it in half? What do you get? Okay. 54 is pretty close to doubled of what? 27, isn't it? So if you start thinking about it, isn't this the same thing as saying the cube root of 54 times the cube root of 2? Again, 54, if I divide that by 2, what do you get? 27. Okay. What's the cube root of 27? 3. Now, what's left underneath those radicals then? 2 times 2, which would be 4. So this would simplify itself out to becoming 3 cube root 4. Again, if you just start looking at the 108s, cut it in half. Cut it in half again. See if you get down to a 27, an 8, a 64. You're trying to see if you can fall into one of those. You know that it can't be any larger than that because 5 cubed is 125. They go so fast by getting so large. A lot of times you're looking for 3s and 2s. Okay, just because the numbers get so large so quickly. All right. Try to look. We know how to. What's the square root of 12 in simplified radical form? 2 or 3. Okay. Again, 54. We just did an example of that. What breaks that down? It's 27 and 2, isn't it? So that's 3 cube root 2. All right. Now.
No.
But here's the thing. You just did this. We just did this. We did this a second ago, but we did it in terms of exponents. A fifth root is what exponent?
1/5.
1/5. Now, since it's a fractional amount, can't I put that at the top and bottom?
Yes, you can.
Okay. Let me move this up a little bit here. So, since this is a fifth root, that's the exact same thing as saying 3 to the 1/5 over 4 to the 1/5. Okay. How many more fifths do you need to create a whole in the denominator? 4 of them. So I'm going to multiply by some factor of 1, and this factor of 1 just looks pretty crummy. 4 to the 4/5. Okay? The denominator now, the denominator, not the denominator, It has the same base, doesn't it?
Yep.
All you have to do is add your exponents. What's 1/5 plus 4/5? 5/5, otherwise known as 1. Which means your numerator is 3 to the 5th times 4 to the 4/5. You can't combine those because they have different bases. All right. Again, it is so much easier. You can do this with nth roots if you want. But I'm going to say stay away from the nth roots. Go to the fractions because fractions are easier to see. They're so much easier to work with in this case. Right? I won't make you switch back to this. I will have you guys automatically take any nth root, and I want you to get the habit of switching it to fractions and working with the fractions. It's cleaner. There's no reason to switch it back then. Right? Oop, just did that.
No.
Well. Alright, so basically what we're gonna do.
What do you think you're going to do?
Well, I'm thinking.
What's that?
Okay,
Thinking about it.
Inside the parentheses, same number.
Okay.
It's like square roots, right? So you can just add them together. They have the same, they have the same.
Correct.
You can just add them.
Yeah. Which is? 9. Yeah. Notice, since these two guys here are the exact same thing, isn't it the same exact problem if you think about it? Isn't that the same thing? It just so happens that the x value just looks like crap. Seriously. You're just combining like terms. If you have like terms that you're multiplying together, in this case it's the 5th root of 6, it's the same idea. If this happened to be 7 square root 2 plus 2 square root 2, what would you write? 9 square root 2. Okay? The only thing that's different now is that this is 7 5th root of 6 plus 2 5th root of 6, just written differently. So all you have to do here is combine like terms. You get 9 times 6 to the 1/5. And that's all you have to do. Okay? There's no other simplifying or anything needed, right? All right. Now, in this one, though,
Yeah.
what would you have to do first? Do you have to?
But it's cleaner.
In this case, I don't think it's any cleaner to go with fraction because they're cube root of 16. What's the cube root that's hiding in the 16? 8. And that's a dead giveaway because what are you subtracting on the other end? The cube root of 2. Because isn't the cube root of 8 times the cube root of 2 the cube root of 16?
Yeah.
So what's the cube root of 8? 2. So this is 2 cube root 2 minus, well, what's the coefficient out in front of that cube root of 2? Yeah, it's a 1 cube root 2. I wanted to make sure I showed you that there's a 1 there because some of you guys might actually just say your answer is 2 because you think that those back ends just subtract off. They don't because they're still just going to be in the treatment like they are variables. Your answer would be, well, 2 minus 1 is 1, so your answer is cube root 2. Okay. Sometimes you have to search and simplify, but a big dead giveaway is going to be one of them is probably the one you need to get it in terms of. Okay? Here you go from there. On this one here, it's on page, 411. I have the PDF already up there. I think I had you guys doing 24. I think the other part got cut through. 24. Yeah, go 24 to 54 evens. right, it's like 16, but a lot of them are pretty straightforward. Remember, no fractional exponents are allowed within the denominator. Everything has to be rationalized, if you will. Also, you should have absolutely positively no decimals. Everything should be in simplified radical form as this stuff goes through. Okay? Obviously, some of these solutions you could get 3 for an answer or 7, something along those lines. It's possible, but a lot of them will have some exponent stuff to work through. When you get to ones like number 48, you've got that 4th root of 80 over 9. That's the type that I would switch it to the fractional exponent and rationalize, because there's really nothing else you can do with that. Okay? And go from there. El Maco Senso? Yay! We'll do exponents, we'll do variables tomorrow. That's when it gets interesting. A little messy tomorrow.